Hi, welcome to lesson 14.3. We've finally reached partial derivatives, so this is going to feel like a calculus class for real now. We want to dive right into what this means because we know what it is to take a derivative, and we've worked with the definition of a derivative for a long time now. So we're going to use that here and talk about taking partial derivatives, which means taking a derivative in the direction of x or in the direction of y, and ultimately in any direction. So take a look at a very familiar expression right here. We have a difference quotient, and we use this curly little d, not a regular d, but a little curly d, to indicate it's a partial derivative. So if you use straight up regular d's here, it's going to look wrong, and it's going to be confusing when you are taking derivatives that aren't partial in a side-by-side situation. So make sure you're using the right symbols. So we have a partial derivative of a function of x and y with respect to x evaluated at a certain point, x naught, y naught. So here's our symbol for that. This vertical bar indicates that you're going to calculate the value of the function at a certain point. And so we have x naught plus h, and we're holding y naught constant. So you're treating y naught like a constant. Now let's come over here and look at what this actually means. If we are looking at in the x direction, so here's our x-axis. We have this blue trace on the surface of our function, and that is a curve that is parallel to the x-axis. And we draw a tangent line to that curve at the point x naught, y naught. And the partial derivative is going to give us the slope of this line with respect to this curve. Alrighty. We have a very parallel situation down here, the partial derivative of f of xy with respect to y, so in the y direction at this same point. So we come over here and we have a portion of this same function, the gray surface here, and we draw the blue trace, a curve that sits on that surface, and then the pink line, or red, depending on your screen resolution, is the tangent line to that blue trace curve at the point x naught, y naught. And then we get the rate of change of this function in that specific direction along or parallel to the y-axis. So let's put these pictures together. So here are both of those pictures together, and here's the point that was common to both of them. And when you look at the two red lines, they seem to form a slope, or a plane that is tangent to this surface at that point. So that's what's going on here visually. What we're doing when we take a partial derivative is focusing on one direction at a time. So we have lots of different symbols for partial derivatives. You just saw the curly d, so partial derivative of f with respect to x. You could also put f sub x. I like that one myself. It's much less writing. You could put dz dx if they've called the function z equals. And this is only if you want it evaluated at a certain point. Here we have a regular d, not a curly d for partial derivative. And how do we know this is a partial derivative? Well, they've got y naught being held constant and x being allowed to be whatever it needs to be as you calculate it, and you're going to calculate it as x goes to x naught, basically, as a substitution value. So you're evaluating it in the x direction. So I like f sub x. The curly d's are very common. If the function is called z, you could do z sub x or dz dx. All of those are in the x direction with respect to x. And by the way, when I write notes, the phrase with respect to comes up so often, I just abbreviate it WRT, so with respect to x. Down here, a very similar notion, partial derivatives with respect to y have the exact same forms, just with a y instead of an x. I particularly like the really easy to write ones myself. Okay, so moving on, we're going to just take some partial derivatives as practice now. So find the values of the partial derivative of f with respect to x. That's how I read that phrase. The partial derivative of f with respect to x, and the partial derivative of f with respect to y at the point 4, -5. So I'm going to find df dx and evaluate it at 4, -5. So that's how I would set up the problem. Please be showing work like this, like I'm demonstrating to you when you do work for me. So with respect to x means we treat y like it's a constant. You've done stuff like this when you've done implicit differentiation, so it's not totally new. But here we go. X squared, the derivative of x squared with respect to x is 2x. All right, y is a constant, so the derivative of 3xy is 3y. And the derivative of y with respect to x, well, since y is being held constant, the derivative of a constant is 0. And -1 is a constant, so its derivative is 0. And we have our partial derivative with respect to x. We're going to evaluate that at 4, -5. So now we just do substitution. And that's going to be 8 minus 15, or -7. So there's our first partial derivative. Now we need to do the partial derivative with respect to y, evaluated at the same point. Okay, so looking again, now we're holding x constant and taking the derivative of the function with respect to y only. Well, this has no y in it, so it's a constant, holding x constant, so the derivative of the first term is 0. Then the derivative of 3xy with respect to y is 3x, treating x as a constant there. The derivative of y is 1, and the derivative of a constant is 0. So we're going to evaluate this at the point 4, -5. And that's going to end up being 3 times 4 plus 1, or 13. So there's our derivative of f with respect to y. So that's pretty straightforward. Just going to do some more samples so you can follow along and it makes sense to you. Here we've got a function times a function, so we're going to end up using the product rule. So the partial derivative of f with respect to y, or in the y direction. Now notice they did not ask us to evaluate it at a point, so we will not need to put that next symbol in. So product rule, uv prime plus vu prime. That's how I memorized it since I was a kid. You might have memorized it backwards, and that's fine because it's still the same thing with addition. So the first function, okay, with respect to y, the first function is y, the derivative, okay, so y. Then v prime is the derivative of the second function with respect to y. That's going to be cosine of xy. And then the chain rule applied to xy, the derivative of xy with respect to y is x. Okay, then v, the second function, times the derivative of the first function, derivative of y is 1. So please clean these things up. If you would like credit for having completed it correctly, you'll clean things up and make them neat and easy to read. Sometimes it's just better to put arguments of trig functions in parentheses so it's clear what you're taking the cosine of. And then sine of xy. I want to remind you that when you are taking a test or quiz and someone is having to read through your handwriting to award you points, if you make it easy for them to read, you earn more points. Alrighty. So messy answer, but that's what it is. And this is a section of the text in this class that people tend to like because it's calculation based and what you're probably historically very good at. For a lot of folks, not for everybody. Some people are plagued by small errors that they can't seem to get rid of, but a lot of my more advanced students really like this part because it's very, very, it moves a lot. All right, find dz dx if this equation defines z as a function of two independent variables x and y, and the partial derivative does exist. Okay, now solving for z is a headache here. It's one way to go, and it would be easier to take the derivative of a function if it was in the form z equals some kind of function of xy, but it's not. All right, so we're going to differentiate both sides with respect to x, holding y constant, and we're going to treat z as a differentiable function of x. Shall I repeat that? we're going to differentiate both sides of the equation with respect to x, and we're going to hold y constant. And we're going to treat z as a differentiable function of x. This is implicit differentiation, if you've forgotten about that. So let's look at the left. With respect to x, okay, holding y constant. So there's no x here, and, well, let's write it like this. dz dx. This is symbolic form of what I told you we were going to do. Okay, that's what we need to find. So we need to do d dx of yz, and we need to do d dx of the natural log of z, and that's going to be equal to d dx of x plus d dx of y. Okay, so look at this one. So y is a constant, so it's going to be out front, and then we've got dz dx. Some people like to put z prime. I find that confusing in multivariable calculus because I like to see what it's with respect to. So now the derivative of the natural log of z is 1 over z. And then chain rule says dz dx, just like in the first term. Okay. d dx of x is 1, and dy dx, since y is being held constant here, is 0. And now we see we can actually solve for dz dx. If we're going to factor on the left, dz dx times y minus 1 over z equals 1. So now we're going to get dz dx equals 1 over y minus 1 over z. Please do not leave a fraction in a fraction, ever. I'm going to multiply top and bottom both by z to get rid of this complex fraction. We're going to have z over yz minus 1. There is the derivative of z with respect to x. That might take a little practice, actually, to become comfortable with that calculation. All right, moving on. Okay, so got a kind of an interesting function for you. Let's see if you can picture it as it's described in the problem before you dive in. This is an exercise I want you to do constantly, even when they don't ask you to picture it, because you're going to need this skill. The plane x equals 1 intersects the paraboloid z equals x squared plus y squared in a parabola. Find the slope of the tangent to the parabola at 1, 2, 5. All right, can you draw this? Now, a paraboloid is a bowl, and this one has not been shifted off the origin, so it's a parabolic bowl sitting at 0, 0, opening upward. And I'm going to come down with a plane, 1 unit, and if you draw your three-dimensional axes like this, with this one being x, here's x equals 1. We've got a plane coming down, parallel to the y-axis, chopping into that paraboloid. You could just do a rough sketch. So here's a parabola that's chopping into our paraboloid, and I didn't do a good job of drawing that at all. I need to do much taller. So this plane is chopping through our paraboloid, just chopping a piece of it off the front, okay? And since this is sitting at 0, 0, the vertex of the paraboloid here, and this is going through 1, this isn't going through the middle of the bowl. This is just chopping off a parabolic piece right here, right there. Okay, really bad sketch, but you don't need a great sketch to help you visualize it in your mind. But let's look at their beautiful drawing, okay? Actually, let's just delete that. There we go. And here's what we've got. Okay, so not a good drawing, but it was enough to help me visualize it. We've got a bowl sitting at the origin, and you can see the bottom of the bowl. It's hard to picture. I don't think they drew it to look like the bottom of the bowl was at the origin, but I don't know if that's just me or not. Here, however, is the intersecting parabola. The parabola that's created by the intersection of the paraboloid with the plane that goes through x equals 1 right there. Okay, so there's x equals 1, and so there's this piece of bowl that's sticking out on this side of the plane, and they want the slope of the tangent to the parabola at 1, 2, 5. So they drew you a picture of this. There's x equals 1 over 2 and up 5. That point is sitting on that blue parabola right there, and they want the slope of this tangent line. So my question to you is, could we do this as a one variable calculus question and save ourselves some trouble maybe? I want you to think about it. Actually, I have this on the page in front of me while I'm doing it. If this is a one variable calculus question, then we wouldn't have x and y. We know along this parabola that x is 1. So I'm going to substitute in 1 for x squared up here. Okay, so 1 squared is 1. So this is a one variable function. Z is 1 plus y squared. So if we want dz dy, not partial, dy, as if this was strictly in the two-dimensional plane, x equals 1, all right, we could do the derivative is 2y. And if we're going to evaluate that, where y is 2, then that's going to be 4. So the slope of the line there is 4. Now, if we're doing this as a two-variable question, partial derivative of z with respect to y, and we're going to treat this evaluated at 1, 2, 5, okay? So the derivative of z with respect to y is going to be holding x as a constant, and the derivative of a constant is 0. And the derivative of y squared with respect to y is 2y, evaluated at 1, 2, 5, and y is 2, so it's 4. So you do get the same answer, and you should get the same answer, but you see how like single variable calculus still covers this. It's just that we're not used to working in the YZ plane in single variable calculus, whereas we actually parallel to the YZ plane, I should say. So it's just kind of interesting that you could do it either way. There are some things you'll learn in here that you can still do with single variable calculus, and people always want to ask me questions in the middle of a test. Well, what if I do this with single variable calculus method? My answer for that question will always be follow the instructions as they are written, and if they do not specify what method you must use, then whatever method you use, is the answer's right and the work is shown, you will get full credit. So these methods don't look any different except for the symbols, but they're both going to give you a right answer. So if I happen to say, make sure you do something in a certain form, follow the instructions always, okay? When in doubt, make sure you're following what you're asked to do, and anything outside of that, as long as you show your work, should be acceptable. Okay, so can we do this with more than two variables? Well, very much certainly yes. Oftentimes when we have a function of three variables, we'll call it W. They didn't happen to do that here, but if I do this, I could also say find the partial derivative of W with respect to Z in this case, put it over here with respect to Z. So I want you to recognize that as a possible way to write this. And three independent variables, the derivative of our function with respect to Z means that X and Y are constants. So hold those constant, and we don't have to evaluate it at a certain point. So Z is the only variable in the expression. Well, X is a constant, so it would come along for the ride. Z is the argument of sine, so we have to take the derivative of sine and say cosine of y plus 3z. And then we have to do the chain rule. The derivative of the argument with respect to z, well, this would be 0 plus 3. So times 3. So we have 3x cosine of y plus 3z. By the way, if you have numbers multiplied by a trig function, don't leave them in the back. That's actually very hard to grade and notice. So please put all coefficients of trig functions in front of them because oftentimes this gets mistaken for part of the argument. So there is the answer to number 6. All right, I want you to try number 7 on your own. I'm going to peek at it real quick and say it's a physics question about electricity and resistors. And the sneaky trick to it is implicit differentiation. So I want you to give that one a try on your own and then check the book and see how you did. Okay, so let's look at example 8. This is an unusual function, so I want us to use this to talk about continuity in three-dimensional graphs, so as it relates to partial derivatives. So this is where we deviate from single variable calculus where continuity and derivatives are concerned. So they've picked a very unique function. I want us first, we have to figure out what this function looks like. So we've got f of x and y. It's a piecewise function. It equals 0 where x and y are not 0. And it equals 1 where x and y are 0. So this is a constant function, but it's got two different values. So we've got the xy plane. I don't know if you can see me moving my hands around while I talk very well in a little bitty window, but you've got the xy plane, so picture that in your mind, and z coming up out of that xy plane. And that is the function where x and y are not 0. Well, where is xy equal to 0? Well, anywhere that x is 0, so that's the y-axis. And anywhere that y is 0, that's the x-axis. So this is the entire xy plane except for the axes. That's the top part, the 0. Okay, well this function then is equal to 1. You move up 1 unit along the axes. So where there are gaps in the plane down below, above those gaps hover 2 lines. In fact, in the book, they label line 1 is parallel to the x-axis, and line 2 is parallel to the y-axis, 1 unit above the xy plane. So can you picture that in your head before we cheat and look at the picture? Not really cheating, but you get my point. I need you to be able to visualize these things. So here we go. I was sneaky and hid the box. So we've got the xy plane in blue except for the axes, and then 1 unit higher, we've got line 1 parallel to the x-axis and line 2 parallel to the y-axis everywhere that xy equals 0. So this is a very unusual function. Clearly, when you look at the picture, you see that there are discontinuities. But does that mean it's not differentiable? So we got to tackle these two topics as they go together. So we're going to do the first thing here, find the limit of f as xy approaches 0, 0 along the line y equals x. So I want you to picture the line y equals x here, and from this angle it's a little bit more awkward than if it was a flat drawing. So there's the line y equals x. We're approaching the origin along that line. And so for the a part, we've got the limit of f of xy as xy approaches 0, 0. But we're doing this on a very specific pathway, y equals x. Okay, so we're headed toward, and it's sitting on the plane. So this line is in the plane, so the function value is 0, and then we hit the origin, and the function ceases to exist. But it's headed towards 0, 0 from this direction. From this direction, it's headed towards 0, 0. It's headed, or z is 0 along this line, lying in the plane. And the function doesn't exist at 0, 0 on this plane, but it does exist up here. However, we're examining along this pathway, y equals x. So even though it doesn't exist at 0, 0, that's where the line is headed from both directions. So that is just the limit of the function of x and y as xy heads to 0, 0, 0. Pardon me. And this function, instead of writing f of xy, I really should have written just 0. That's what the function value is as we approach the origin along the line y equals x, and that's just going to be 0. Okay. Second part, prove that f is not continuous at the origin. Well, a picture is not proof. We're talking algebraic proof, and so if it has a limit somewhere that's not equal to 0, then it's not continuous. So can we go somewhere to find a limit expression that is not going to be 0 when it's evaluated? Make sure I'm looking at my notes explaining this well. So our function value at 0, 0, we said is not the origin, because of our extra little rule up here, if xy is 0, which in this case it is, then the function value is 0, but the limit over here, oh, excuse me, but since xy is 0, we pop up here. This is where it's not 0. I spoke backwards. 0 times 0 certainly is 0, so our function value there is 1. And if we take the limit of our function as we approach 0, 0, but we do so along these lines, then we see that we reach a value of 1. And so the function is 1, but the limit is 0, therefore f is not continuous. And finally, C, show that both partial derivatives exist at the origin. So here's where we depart from single variable calculus. If we're discontinuous at the origin, the limits exist, but frequently, trying to get the idea of a tangent line where a curve doesn't exist is impossible in 2 dimensions. But let's look at this. You just have to think about it a certain way for this to make sense. And I had to read through it several times to make sure I could explain it, and I still might be awkward. So make sure you read through this on your own and make sure it makes sense. So we want the partial derivative of f, sorry about the handwriting, I hate these boards, with respect to x at 0, 0. Okay, so we're going to hold y constant. So y is a constant, constant at 0. Okay, so the 0 here is our y value. We're holding constant because we're doing this with respect to x. And so our function value, well, since y is 0, is going to be 1. Okay, for all x values. So the graph, if you look at this, where x is 1, where y is 0, is the x-axis. All up and down here, the function value is up here at line 1. So the function is just L1 when we hold y equal to 0. And the slope of that line, with we're saying how it changes, how z changes as you travel along different values of x. Well, this is a flat line. It doesn't go up or down with respect to z. So it's got a slope of 0. So our derivative is 0. You have to think through that. I'm going to say it for the other part, df dy now, same argument. So think through it again as I say this, at 0, 0. Okay, now with respect to y means in the y direction, which means that we are going to be holding x constant at 0 as we explore different y values. So all along the x-axis, the y values are, all along the y-axis, the y values are changing while x stays 0. And that puts us up here at line 2. Our function, if we hold x constant at 0, is just this line. And this line is not increasing up the z-axis at any point, so its slope is 0. Okay, so its value is 1 because it's sitting up here, but its slope is 0. It's a flat line. It doesn't increase, the z value on that line does not increase or decrease anywhere. It stays at 1, and so the slope is 0 even though the value is 1. And that is a really awkward question to think through. So make sure you spend some time thinking about that one, picturing it, describing it, and understanding what I just said in part C. Okay. Now you can take second derivatives and third derivatives and fourth derivatives. There's no limit on how many derivatives you can take, just like in single variable calculus. But let's look at all these wacky symbols, okay? This symbol confuses people. So I'll tell you where it comes from. If I have the partial derivative of f with respect to x, okay, this is like saying d dx of f, okay, and then I'm going to take another derivative, d dx. We see how the d is repeated, so they do d squared of f. And then dx times dx is dx squared. And I have a hard time with this symbol because technically that means there's parentheses here, but nobody writes those parentheses. So this is a confusing symbol. You get used to using it, and it doesn't have to bother you anymore. or doesn't have to bother me anymore, really. But that's where it came from, and that's what it means. So don't get too caught up in notation. I personally prefer this because it's just easier to write, and I don't accidentally put the little symbolic exponents in the wrong places, okay? So a second derivative with respect to y each time would be fyy as subscripts. Now, you don't have to take it in the same direction both times. You could take the first derivative with respect to x and the second derivative with respect to y, and then vice versa. And I like the shorthand here too. The order of the subscripts tells you the order to do the derivatives in. So let's do this and see this in action so it makes sense. Not hard, just the first time you do it, you want to see an example. So I'm going to do the partial derivative of f here with respect to x. So going through, with respect to x means y is a constant, so cosine of a constant is a constant, and the derivative is going to be cosine of y. And then the derivative of y e to the x with respect to x, y is a constant, and the derivative of e to the x is e to the x. Okay, so if I do the second derivative of f with respect to x both times, see, I have the habit that I want to draw the parentheses, but you don't have to. Okay, again with respect to x. Well, now this is just a constant, so its derivative is 0, and y is a constant multiplied by my function e to the x. Derivative of e to the x is e to the x. So there's our second order derivative. Okay, now with respect to y, so that takes care of that one. With respect to y now. Okay, over here, x is being held constant, and the derivative of cosine y is negative sine y. All right, derivative with respect to y makes e to the x a constant, and there we go. And so the second derivative of f with respect to y both times up here, that means we have to take the derivative of sine y with a constant in front of it of negative x. So negative x cosine of y. My notebook just fell. And then the derivative of e to the x with respect to y is a constant. So this is our entire second derivative, and that takes care of that. And then we have to take second derivatives doing one of each direction. So here's my df dx, and so now I can do df dx first, and then second time dy. So I'm going to do the derivative with respect to y of this expression. So that's going to be negative sine y, and the derivative of y e to the x with respect to y is e to the x. And then we're going to do the partial derivative of f. Over here I did that one, and now we got to do the one with y first. dy first, so we'll use that as our first derivative. And then with respect to dx, so here, negative sine y is a constant multiplied by x, and with respect to x is e to the x. And I'm wondering if you've noticed anything. Check this out. Does the order of taking derivatives matter? Now, I know this is not a proof, it's just a demonstration, but your theorem here is that second order partial derivatives doesn't matter whether the order is xy or yx are equal to each other. Okay, so they state it with all the fancy details put in here, but it should not matter the order it was taken in, they should be the same. So we want to take one of these as practice down here with respect to x first and then with respect to y. But if you mistakenly did it in the wrong order, you should still get the same answer. I've got to take the first one first with respect to x. Okay, over here, y is a constant, and this expression doesn't have x in it at all, so its derivative is 0. And so if we do our second derivative, dx dy, well, of this is just going to be 1. So happy day. They're not all hard. You could propose going about this this way. Can you come up with a really good reason not to do that? What do you think? If you have to pause it and think about it, go ahead. All right, I'm going to assume that you thought about it, and I really don't want to have to do quotient rule on the second term, e to the y over y squared plus 1. You can do that if you really, really want to, but then when you go to take the second derivative, you've done that one the hard way, and then dx, only one term is going to have an x in it at that point, and no matter how much work this was to figure out the derivative of this with respect to y, the derivative of that with respect to x is just going to fall out and be 0. So yeah, there's a hard way to do things. You do not have to do them in the order you're given if you know the order doesn't matter. Okay, remember that on tests because it saves you a lot of time. Alrighty, so this is just kind of warming up for linear approximation. I'm not going to do a ton of that, so I want to make sure I get a definition of differentiability in here in general, and then ask you to focus a little bit on theorems 3 and 4, and we'll unpack those better in the next section. But we want to define differentiability. So a function z equals f of xy is differentiable at a point if the partial derivative with respect to x at that point and the partial derivative with respect to y at that point exist, and delta z satisfies an equation that looks like this. Okay, so this seems far-fetched to need something quite this complex, but it's going to relate to linear approximation. If you remember that in single variable calculus, it looked similar. Here we've got the rate of change with respect to x times the change in x, and we're adding that to the rate of change of y times the change in y. So we're approximating the change in our function by approximating how much change has taken place in the xy direction separately. And then we have these two extra little terms with epsilons hanging out down here. Let's look and see what those are about. So in which both epsilons are approaching 0 as both changes in the x and in the y are heading to 0. So these are little bitty terms, differentials, that are teeny tiny, and as long as they're headed to 0, then we have a nice approximation here for our change in our function value. And this is, it says we call f differentiable if it's differentiable at every point in its domain. So this whole definition is just differentiable at a single point. And so we'll never be able to prove it's differentiable at every point. We would not have enough time to do that. But we will be using this for linear approximation, and you know, you'll see where the little extra terms come in there. I think it makes more sense after we do that. But if a function is differentiable at every point on its domain, it's a nice smooth surface. So in 3 dimensions, when we have jagged, pointy surfaces, there's not a lot of differentiability. But that's very similar to single variable calculus, because you learned that like cusps aren't differentiable, sharp corners in a function aren't differentiable. So this is the 3-dimensional equivalent. We know when we have a smooth curve, it's differentiable in in single variable calculus. So in multivariable, when we are differentiable at every point in a domain, instead of being a smooth curve, it's a smooth surface. So once you review these 2 theorems, we'll unpack them better in the next or when we do linear approximation. But here's the guide. Differentiability implies continuity. All right, so we will use that at more length later. I just wanted to introduce you to this definition right here at the end where we're talking about continuity and differentiability. All right, thanks for listening.